Hi everyone, my name is Andrew Litteken. I work on compilers and optimizations for quantum computing at Intel, and I'll be talking about using LLVM as a quantum intermediate representation and the benefits and challenges that coming from using it that way. So I'll be talking about three different aspects of using LLVM as an intermediate representation. The first is the set of constraints that we have on quantum compilation and how we can use LLVM to satisfy those constraints. The second, how we can alleviate some of the difficulties that these constraints put on higher level programmers. And then finally, how we allow the quantum audience, who oftentimes are not compiler experts, to still adapt and use our compilation framework to develop their own quantum optimizations. So I'm not going to go into too much detail about quantum computation, and we don't really need to understand the mathematics or mechanics behind it beyond a few simple terms to really understand what we're going to talk about in this talk about. So a quantum program acts on qubits over time, and the qubits are represented by the horizontal wires in this image. And then we apply the single qubit gates, which operate on one qubit, which is the unit of computation for quantum computing. And then there's multi-qubit gates. And so in this image, gates are applied from left to right, like a classical circuit. And altogether, it's just called a quantum circuit. So these are mostly all the terms that you'll need to understand for what we need to talk about in a quantum compiler. So taking this circuit from a programming language to running on a back end, such as a physical device like the quantum chip, or a simulator like a supercomputer, or potentially even your own laptop if the program is small enough, is a multi-step process that imposes many compilation restrictions that must be considered due to the limitations of the devices. So we'll be mainly focusing on the LLVM-based quantum compiler that's in the Intel Quantum SDK. But to understand the design decisions, we're going to talk a little bit about the rest of the components in the pipeline real fast. So the main front end we have is a C++-based hybrid quantum classical programming language that Intel gives users through the Intel Quantum SDK. And then our quantum intermediate representation is essentially LLVM with quantum intrinsics added to it. And like LLVM as a whole, it allows us to develop different front ends, including Intel's own OpenQASM front end, which is a portable circuit representation. And then we take that and we translate it to our quantum intermediate representation. So the compiler handles most of the legwork in terms of reconfiguring and normalizing the quantum program to fit the restrictions and requirements of the rest of the quantum stack. At a high level, this means that we have classical code that's going to be in the runtime that we just use classical compilation on. But it also means that we have to extract quantum instructions from the rest of the program, use architectural information about the physical device or the simulator to match the connectivity restrictions of the device. So like similar to how there's a limited number of registers, there's a limited number of qubits, and only certain qubits can interact with other qubits. So we have to match those restrictions. Then we also want to reduce the quantum resources used by the device. The more you use the device in the near term, the more likely it is that a program will fail, and we want to get around that. Then the quantum compiler eventually generates the program in a quantum ISA, and these quantum components are then linked into the rest of the binary, which allows it to be accessed later by the runtime. While some of the abstractions that we use in the quantum compiler are general to quantum computing as a whole, we do have optimizations and a specific ISA that is best used on Intel backend simulators and hardware. When the program is run, it invokes the quantum runtime. This processes the quantum ISA, deploys the quantum programs to the device, and processes any measurements that return. Only at this level at the quantum runtime can we run any classical components in between quantum instructions. Since this runtime and processor is often spatially and temperature-wise, from like room temperature down to around absolute zero, and due to low lifetimes of qubits on quantum devices, this effectively means that entire quantum programs, the pieces of quantum programs, cannot require any classical operations to reproduce their result. The quantum instructions are passed through the control electronics to the quantum device. And here the instructions actually perform the execution. We can't have any, like I said, we can't have any conditional execution or classical instructions before they are returned back to the runtime. This inability to perform conditional execution, even based and even based on user input, will be a crucial part in how we have made our decisions in the Intel quantum compiler design. So just to sort of reiterate and break it all down, the main challenges our compiler faces that we can't have branching in the quantum instructions. We need to reduce the number of quantum operations that we use and match the device constraints, as well as not have any classical operations in quantum code. I will caveat this, that a lot of these decisions are based on today's quantum technology. They are not necessarily going to be forever, and that's something that the entire field and Intel is working on and changing. So I'm going to start by talking about how the compiler leverages LLVM to match these constraints. So this is an example of what a user can write using the Intel Quantum SDK. The quantum kernel attribute to a function denotes, as a section attribute that we pass down through the compilation process, and denotes that this section should be treated quantumly. It needs to be treated differently than the rest of the compilation. We have qubit types we have the qubit type and c-bit types, which are just over particular integers that denotes that this is a viable piece of data that we can perform a quantum gate on. And then we have a header file that has a lot of different quantum operations that are standard for quantum computation. What exactly they're doing is not important, but it just lets users actually define quantum algorithms. Then we have the classical component. The entire kernel can be called as by a classical function, which gets extracted and handled and then is called by the runtime later on by pointing to the blob of quantum instructions. At this level, the program is able to interact with the quantum data and capture the measurement values and act on them. Several quantum operations are included inside loops and also inside other conditional statements. But we can't have this in the final program. We need to unroll it, and all the qubit arguments in particular need to be known at compile time. Luckily, LLVM's infrastructure does have lots of tools to handle all of this information, handle all of these structures and unroll them. However, these structures are obviously in the classical sides as well. Applying the unrolling operations to every part of the program would obviously be time-intensive and kind of unnecessary. So we use the LLVM path managers to handle these situations. However, we need to satisfy a bunch of different conditions to have a valid quantum kernel at the end. We can't just use a path manager framework out of the box because we might need to go backwards, rerun operations conditionally. Previously, this was kind of done at the beginning, using several calls to just the opt tool to run different pieces multiple times. But now we have 5 different managers and our own driver to actually achieve this. The first driver just replaces the header file declarations with quantum intrinsics, and then recursively inlines quantum kernels, so that way that the unrolling and the constant folding operations are able to have all the information they need to fully unroll the circuit. The second, third, and fourth path managers are actually rerun several times, and is the portion of compilation that uses the LLVM passes the most, and they are restricted to quantum operations only. The middle loop unrolling constant folding passes are only the function passes that are only run on quantum kernels, which, as I said, was denoted by adding that attribute in the front end, and they're checked prior, and any loops that are checked that are optimized are checked prior for whether they even contain any operations, because if they don't have any quantum operations, we don't actually need to unroll them. If a kernel is not found to be valid, we just run a set of passes, very similar to the O1 function simplification pipeline, and this continues until the function is unrolled and unfolded, or until an attempt limit is reached. In which case, there's an error shown to the user that it wasn't fully unrolled, and they need to decide if that was a problem or not. And then we move into the last manager, which is really just the actual quantum handling and the quantum processing that we need to do, which is a set of passes that lowers the mathematically friendly gates that we gave the user down to the physical set of gates that are actually available on hardware, as well as mapping the program qubits to physical locations, moving them around as needed so that each qubit that needs to interact with another qubit can. This is also where optimizations for best performance on Intel backends occurs. So while while the LLVM pass managers have been very helpful to pass information around, we do have our own analysis passes as well, so that way we can have information about the quantum module elsewhere in the program. The quantum optimizations in the final pass manager also need to be able to differentiate quantum types from that are represented as integers from the rest of LLVM. And this is especially true when we have to identify references to quantum arrays and pointers. And with non-type pointers, this has made the task a little bit trickier. The library of functions are basically used as the source of truth. They have these qubit functions that are called by the called by the library functions, and really all they're doing is denoting that the argument is a quantum type. And basically, we're able to mark that with a qubit reference function attribute that we're then able to propagate up the call graph and to determine the origins of each uses at the call site and say that this argument has quantum information. We can do the same thing for global values and allocations, and then we were able to identify certain data types, certain objects as quantum data types, and we were able to perform optimizations accordingly. So moving to the next section, we can use these strategies like annotations, alternative intrinsics, combined with front-end analysis and Clang plugins to give the high-level programmer more tools to easily express their programs. So since we need to know everything at compile time, writing functions that maybe involve something like recursion can require weird tricks with templating to recursively index all the qubits in a program. This is sort of shown on the left. This is more just a standard program. But we could do this with recursion, but it's not possible. It's not possible in a very simple way. So we have the functional language extension for quantum to make it easier. This is a small DSL that helps users express their code more succinctly in some cases, but also allows the compiler to just intuit more information from the program without having to make inferences in the IR at the end. So on the right side, we can have recursive functions now. It's more of a functional pipeline, and these produce pretty much the same circuit. It becomes much simpler for the Intel quantum compiler to reason about the right side because of the primitives that we have there, and we're also able to optimize these programs more efficiently. FLEQ also allows us to have several pieces of classical control flow to be handled inside the compilers as well. And an example of this is having rudimentary string processing and to have some on-the-fly adaptation during the compilation steps to different inputs. Since the quantum expression, which is the QExpert type, we need to be able to pass that by value. They're treated as integers within the C++ environment, and this could be difficult to do at only an IR level because it could be converted or some operations potentially optimized away. But we can use Clang plugins to do some of this processing in the front end. So basically, we can adapt the AST by looking for certain binary operators and replace them with specific header file functions, shown here. It's just replaced with a specific function call that and a user could just call this function directly, but we want to make the programming environment the best experience possible. And this also let us have the best programming experience, the easiest programming experience for our users. And so this also allowed us to provide better error messages for users than we would also be able to do at just the IR level by having this Clang plugin. We replace several different operators with quantum-specific calls. And while this is a relatively simple action for the front end, being able to ascertain these actions at the Clang level rather than the IR level allows us to do more with the resulting function calls, and is a powerful thing for us and makes identifying quantum actions much easier. FLEQ processing in our LLVM pipeline is really just a pass, as expected. We convert the FLEQ calls to an internal graph, and we perform resynthesis operations, allowing us to reduce the number of gates and the length of the circuits, oftentimes specifically for Intel devices. The ability to infer this from the language rather than the IR is particularly useful to pass more contextual information down than we could have otherwise, which is useful for trickier quantum algorithms. Additionally, this lets us process and infer many top-level operations, such as an inverse operation. Quantum computing is a reversible. It has restrictions making it a reversible computation environment. And without something like FLEQ and the Clang plugin used to identify the unary operators to do this inverse operation, it's actually very hard for us to deduce without it being handwritten, where to do this inverse operation. So while we have to step slightly outside the standard LLVM pipeline to get more power, the SSA form lets us build concise operation graphs of a quantum program and perform optimizations, and it remains flexible enough LLVM remains flexible enough for us to perform these optimizations and changes in form. So the last challenge is not super technical, but it is more of a human problem. The fact that that compiler developers, in the same way that compiler developers don't necessarily need to know about quantum computation to write pieces of the compiler, physicists don't want to know about compilers to write an optimization. But we still want to make it easier for them to use the compiler stack. So this is an example of just a very simple quantum program written in the Intel Quantum SDK, compiled to LLVM, and then on the left side is the circuit structure that was shown before. The LLVM code can be somewhat inscrutable for someone that is not very familiar with it. And then also many quantum optimizations are written using this abstraction of the quantum circuit. And so while we can get the same information out of the IR, it's a lot of bookkeeping. You have to understand how to track the qubits and how to track the data throughout the different function calls. And we want users developing optimizations for the Intel Quantum SDK both inside and outside of Intel. There's a lot of physicists or people not familiar with these computer science concepts. And so an important part of having them develop optimizations is meeting them where they are. So this is similar to something like Cirq or Qiskit, if anyone has seen those. We have a graph-based structure representing the quantum circuit. Each basic block that contains quantum operations has a graph, and this graph only contains the quantum operations. Each node is just an operation as a quantum operation, and then each edge is the shared qubit between the two options. So you can see like the prep Z operation goes to the Hadamard, and then the prep Z on Q1 and the Hadamard on Q0 both go into the CNOT operation. These dependencies just inform the order of execution of the operations in the circuit. So it's easy enough to translate from the IR to this, but we want the users to be able to manipulate this without having to actually handle anything in the IR itself. And since we have this more restricted mode of having just the quantum operations, we were able to provide a bunch of standard graph operations that will be able to be translated into the IR itself, mainly involving handling the parameters past each gate. So just as a simple example, let's just do insertion. If we had a CNOT operation on qubit 1 and a new qubit 3 that's not in the graph right now, we want to add it before the CNOT operation on qubit 0 and 1. So the user can call a create method for a quantum operation, like they do for an instruction in LLVM. This instantiates a new instruction and ensures the quantum and gives the quantum module ownership for the sake of memory management. Then they can use an insert method on that new operation to put it in after the prep Z on Q1. So we do several things. The first is to update the circuit object as you'd expect for a graph, for a DAG. And then we add this to the IR as well. We have to change the IR as well. So this is seen in the simplified form. The purple box is the new instructions. It's adding that CNOT operation and the addressing for qubit 3, but then it also has moved the addressing for qubit 0 above the CNOT operation for the prep Z. This is extra handling that we need for LLVM, but it's not really something the optimization developer necessarily needs to worry about. Let's them use the power of LLVM, but only focus on the requirements of the quantum algorithm. There's other operations, and there's other things. This can be embedded inside many a parent function of a quantum kernel, but I'm running out of time, so I'm going to skip this part for now. So wrapping all this up, using LLVM is a powerful piece of the Intel quantum compiler lets us combine classical computing with the needs for quantum hardware. Clang plugins and the modularity of the LLVM path system lets us have unique optimizations and language opportunities to higher level developers through FLEQ. And even through this, we want to provide tools to manipulate our IR for optimization. And we provide that through the quantum circuit object, in an attempt to essentially to create a domain-specific version of the IR that only touches the quantum pieces for those developers. Lastly, many of these pieces are open source. We'd love feedback and contributions from the wider community for how we can do better, in particular, like improvements to how we've structured things. We are kind of a team of, most of the team is physicists, so there's been some potentially interesting decisions made. But we'd also love if there's more efficient ways we can be doing using pieces of LLVM or tools we're not aware of, and then also quantum optimizations from researchers using that quantum circuit object as well. That's everything. Thank you for your attention. And are there any questions?
Thank you. I don't know if this works. So, any questions? Yeah, here is a microphone, or I'll pass this one around.
Yeah, thanks for your talk. Enjoyed that. I have a couple different questions. The first is about like your simulator. So, like, what sort of simulators do you compile your IR down to? Like, is it a density matrix tensor network? And then, do you guys have like a cloud system where you support like accelerated or like, you know, high memory backends for those sorts of simulations?
Yeah, so the top QR code is to the SDK itself. That is like run on the Intel Developer Cloud, and so you can run some of the higher power simulators there with more memory and stuff like that. The simulators themselves, there's a couple. I think we have a tensor backend. Then there's some more stripped down ones that like are more. If you're familiar with quantum, like I think Clifford simulator is an option. I don't know off the top of my head which exactly simulators are.
So like Intel maintains their own sort of.
Yeah, we have our own simulators. They're not. They're Intel's based simulators. They're Intel simulators. They're not other people's. I guess so that's the question.
And then, are there any assumptions about like what happens to the state at startup and like shutdown of the quantum kernels? So in other words, anytime like a quantum kernel starts to execute, is it starting at state 0, or are you allowed to like perform some classical computation while like the state is like?
I believe this is something that we're working on to be able to seed it with a state. But in general, I think you should. I think the general. But I think it's done by like using a bunch of prep operations at the very beginning, and then having like whatever operations you need to actually get to that state. Not so much.
Okay, so it's assumed reset to 0.
Yeah, it's expected that you would reset it to 0 at the beginning.
Got it. Thanks.
Hi, great talk. I have a question regarding the quantum circuit object.
Yeah.
So you mentioned that it's embedded as part of the IR properties, or is it something like it's a completely different framework?
It's like on top. It's like something that you feed a basic block to it. It generates this object, and then as you manipulate the object, it will write back what are your changes.
I see. So it's a completely different framework, which takes the IR as an input then.
Yeah, and then like as it changes, it goes back to it. So that way, when you write the module back out, it changes the result.
And is it something available in part of like?
It would be available in the quantum passes section. A bunch of these changes, many of the changes that we're talking about are coming in like a new release. We weren't able to get them out in time for this, but they will be there. The quantum passes section in particular.
And is there like a kind of like the visual representation that we can look at, like whatever is the input to the whatever circuit is, like can you visually see that, or it's like something like a graph and you have to just.
There's no tool for that yet.
Okay, so it's like you have to look through the data structure or whatever.
Yeah, there's no like way to like network, like where Network X has like you can put out the graph. We don't have that yet.
Okay,
thank you. That sounds.
Any more questions? If not, let's thank Andrew again.
So the next talk is